Hey everyone, and welcome. Today, we're diving into a topic that honestly is what separates the good developers from the truly great ones. We're talking about the solid principles. This is all about getting past writing code that just works and learning how to write code that survives.
And that quote just hits the nail on the head, doesn't it? I mean, getting your app to run without crashing is one thing, but building something that can actually handle new features, changing requirements, and the test of time, that is a whole different ballgame.
So that's the big question, right? How do you do it? Well, the answer lies in 5 fundamental principles, all bundled up in this really handy acronym, SOLID.
Okay, let's kick things off with S. This stands for the single responsibility principle. And if you only master one of these, make it this one. I like to think of it with a simpler mantra: one class, one job.
And it really is that simple. It's not one class, a couple of related jobs. Nope, it's one. This is all about forcing yourself to create code that is focused, clean, and super clear about what it does.
So check out this example. It shows the problem perfectly. On the left, you've got this user service that's doing way too much. It's saving users, sure, but it's also sending emails and generating reports. Now, what happens when you need to change how reports are generated? You're editing a class that also handles critical user logic. You risk breaking everything. But look at the solution on the right. So much cleaner. 3 separate classes, each with one and only one job. It's easier to understand, way easier to test, and a dream to maintain.
And this is the acid test. Just think about any class in your project. If a request from the marketing team to change an email template and a request from the database admin to change a table could both make you edit the same file, well, then you've violated this principle.
All right, next up, we're going to tackle O and L together. That's the open-closed principle and the Liskov Substitution principle. Both of these are really about the same thing: how to grow your application without completely breaking the stuff that already works.
So O is for the open/closed principle. And I know, it sounds like a total contradiction, right? How can something be open and closed at the same time? Well, the idea is that your code should be open for you to add new functionality, but closed for modification, meaning you shouldn't have to go back and mess with the core, tested code that you know already works.
Let's imagine a payment system. In the bad scenario, every time you add a new payment type, like Bitcoin or something, you have to go into the main payment processor and add a bunch more if-else blocks. You're playing with fire. It's super risky. The good way? You just add a completely new crypto payment class that fits into the system. The old reliable credit card code, it stays untouched, safe and sound.
And this right here is your gut check. If the thought of adding a new feature fills you with a sense of dread because you just know it's going to break 10 other things you haven't thought of, that is a massive red flag that your design is weak.
And that brings us to L, the Liskov Substitution principle. This one's famous for having the best analogy in all of software engineering. Basically, if it looks like a duck and it quacks like a duck, you should be able to treat it like any other duck, without things blowing up. Any subclass needs to be substitutable for its parent class. Okay, here's the classic penguin problem. So, a penguin is a bird, right? Seems logical to have a penguin class inherit from a bird class. But what if your bird class has a fly method? Uh-oh, you've got a problem, because penguins can't fly. The good design on the right recognizes this. It creates more specific types, so a penguin is never put in a situation where it's expected to do something it physically can't.
And this slide shows you exactly why this is a disaster waiting to happen. Your app has a list of birds. It decides, hey, let's make them all fly. It loops through, gets to the penguin, calls the fly method, and bam, crash. Your program just dies, all because the child class, the penguin, broke the expectations of its parent.
So the big takeaway here is simple, but it's incredibly powerful. When you create a subclass, you are making a promise. You're promising that it will behave just like its parent. You cannot break that promise.
Okay, we're on the home stretch. We have I and D, interface segregation and dependency inversion. Now these two are all about creating smart, flexible connections between the different parts of your code so you don't end up with a tangled mess. This is the interface segregation principle. And really, it's just common sense. Don't force your classes to implement methods that they don't actually use. You want to keep your contracts, your interfaces, small and very specific. The classic example is the old all-in-one office machine. On the left, we've got this one fat interface. It's got everything: print, scan, fax. But what if you're building a cheap, simple printer?
It can't scan or fax. But this interface forces it to have those methods, even if they're empty and do nothing. It's awkward. The solution on the right is just so much more elegant. You break it up. You have separate interfaces for each job. That way, a class only implements the behaviors it actually has.
And this is a hard truth you just have to accept. If you have a huge, bloated interface, it is a design failure. It's a clear sign that you haven't thought carefully enough about the different roles and responsibilities in your system.
And that brings us to our final letter, D, for the dependency inversion principle. Now, this one can feel a little abstract at first, but trust me, it is an absolute game changer. It means your important, high-level code shouldn't be directly tied to low-level, nitty-gritty details. Just look at this flow. In the bad example, your order service is hard-coded to talk directly to MySQL. What happens in 6 months when the boss says we're switching to Postgres? Well, you're in for a world of pain because you have to rip open the order service and rewrite it. But in the good flow, the order service only knows about a generic database interface. It has no idea what specific database is behind it. So you can swap from MySQL to Postgres to anything else, and the order service never even knows. You've inverted the dependency.
And that is the whole point. Your core business logic, the stuff that makes your app special, should not care about whether you're using MySQL or how an email gets sent. It should depend on clean abstractions that hide all those messy details away.
So there we have it. S, O, L, I, and D. We've covered all 5. But let's take a step back from the theory for a second and bring this into the real world. You know, the world of deadlines and daily stand-ups where you actually work.
This is probably the most important thing I can tell you. Solid isn't some academic exercise to get a good grade. It is practical, in the trenches pain prevention. It's about saving yourself, your future self, from those horrible late nights, stressful debugging sessions, and impossible feature requests.
So I want you to take a second and just think honestly about the project you're working on right now. Ask yourself, is your code base, is it hard to change? Or even a simple request feels like it's going to take weeks? Does it constantly break in weird, unexpected places every time you add something new? And maybe this is the biggest one. Does it actually scare you and your team to work on it? If you're nodding your head right now, you are feeling the pain of a non-solid architecture.
So let's end right back where we started. Our goal as professionals isn't just to get the thing running for today's demo. Our goal is to build something that is robust, flexible, and maintainable for years to come. The goal is to write code that survives.